geometry of Bochner curvature of Kaehler manifold. Okay, and this is a joint work with my student R. Kawakami, and so I'm going to talk about. So here is a Bochner curvature. But here is yeah, so this is what I'm going to talk. So covariantly defined double operator closeness of Bochner curvature. Okay. So what is Bochner curvature? Bochner curvature was given by Bochner by himself as analog of wide curvature tensor of Riemannian manifold. And so here is so here is a Kaehler manifold. Okay, and the metric is a Kaehler metric, and so this manifold is a complex manifold, so it has a complex coordinate. Okay, so dimension is n, complex dimension is n. This is a complex coordinate. So this Riemannian metric component. Okay, and the Bochner curvature is how to write here. So Bochner curvature, we write B. Okay, and here. So R means a Riemannian curvature, okay? And here, so, and the R beta bar is the component of Ricci curvature, okay? And also here another so this S is a scalar curvature, but it's just a complex scalar curvature. So this is a Riemannian curvature. Right. This is a Riemannian curvature, and this is the Ricci curvature. This is. Okay, and S is just a contraction. Contraction of the Ricci curvature. So this is a complex scalar curvature, And this is not a scalar curvature in the sense of Riemannian geometry, but this is twice of scalar curvature. Okay. And this is a Bochner curvature. Yeah? And so I want to introduce Delba Nabla, but so these tensors are regarded as so B or R considered as a section, smooth section of the vector bundle. Yeah. So the vector bundle is just the tensor product of the bundle of 1-1 form of ion. This means so here lambda PQ lambda PQ is a bundle of PQ form. Okay. So okay, so is it okay? And so since M is a complex manifold, so there is a how to write? So you consider the usual exterior derivative acting on smooth N form. Yeah. So, but this split into in this way. Yeah. This is just, and this is a Dolbeault operator. But this operator extend, yeah, extend. Or yeah, no. I want to extend this exterior derivative, yeah, for these sections. Okay. So this is just so. But we can extend this Dolbeault. Okay, Dolbeault operator is just PQ to okay. But this can be extend. For example, so here we have a 1-1-M. So yeah. But here we haven't this operator doesn't require any connection, yeah. once M is complex, then this is well defined. But here we need so covariant derivative. Yeah. So how to define this one? For example, psi is this is just yeah, this one. So how to write? So this is but here this is how to write? So this has this sits in this vector boundary. So how to define by in this way? Yeah. So Nabla means covariant derivative in terms of Riemannian metric. Okay, this is a covariant derivative. Okay, this, and here minus sign. So if so, this okay. So if here you have a phi. So phi is so now. So this is just well defined. Yeah, this is well defined, but you need a covariant derivative here. Since this is just a component of this one. Yeah, so we call this covariant Dolbeau operator. Okay. And so this has a nice property. So here is twice of this one. Yeah, but similarly, this also satisfies this. Yeah. Okay. Since so if we take twice covariant differentiation phi, then there appear Riemannian curvature tensor, but the Riemannian curvature tensor is just 1, 1. So this must vanish. Okay. So this gives us so many complexes, elliptic complexes. So you can define any. You can get cohomology group or and so on. Same as in the holomorphic vector bundle valued PQ form. Okay. But here today I want to apply this operator to Bochner curvature. Okay. And also this extend similarly. Okay. And here also, how to write, extend this one. Okay. But this is just a more precisely here. So lambda A and lambda B is a space of complex A forms, yeah, and this space of complex B forms. Okay. Okay, so okay, so we have so here you have no PQ and so if we replace this vector bundle as by holomorphic vector bundle, we do not need a connection. But in this case, this is not the holomorphic vector bundle, so we need this connection covariant derivative. And also, so if we can define by using integration, so this space has an inner product, L2 inner product, then so you can define the formal adjoint of this operator. Okay? Formal adjoint. This is a formal adjoint. This operator. And this there is a famous Kaehler identity. Yeah, here is a Kaehler identity. So here, this is a Kaehler identity. Yeah. But if you put the nabla here, this holds also. And also we take a complex conjugate, then we have a so the second formula gives the formal adjoint of this one. Okay. And here lambda is just a contraction, metric contraction. Just lambda is a metric contraction. So lambda here, I write here lambda. So here, C. So, outright. Yeah, this one. Okay. Okay, so this is an introduction of so covariant Dolbeau operator. Okay. So next I want to, what is this one? So okay. Now we take this, so operate this Dolbeau operator to the Bochner curvature. Yeah, okay. Then we have the following theorem. No. So before giving a theorem, I'll give you some fundamental property of the Bochner curvature. First one is real operator. B is a real operator, so just conjugate. Okay, and also since B is a curvature-like tensor, so this one, and also okay, and the last one is just this one. So this means metric contraction of B identically 0, yeah, vanishes. Yeah. So this is very, very important. Of course, I should mention some geometrical remark on Bochner curvature. If Bochner curvature vanishes, we call Kaehler metric Bochner Kaehler metric, and such kind of Kaehler metric were investigated. Yeah. So, for example, if Kaehler manifold is compact, then Kamishima classified completely, and these compact Bochner Kaehler manifold is complex Euclidean, compact quotient of complex Euclidean or complex projective space, or compact quotient of complex hyperbolic space, or compact quotient of how to write product, Kaehlerian product of complex projective space with complex hyperbolic space. And also Bryant gave some almost complete survey, yeah, on Bochner Kaehler metric. Yeah. Okay. So what is no. So now I'll give you a theorem. So this is a Kaehler. So Bochner curvature is closed if and only if so So these are equivalent, okay, and also yeah. So yeah, so there are 4 or 5 conditions, but these are equivalent to each other. So this theorem said that if Bochner curvature is closed, then it's so closed in terms of formal adjoint. Yeah. So this is very, very, yeah, important, I think. And also this last condition means that so the covariant derivative of rich curvature is represented in terms of so the covariant derivative of scalar curvature. Yeah. Okay. And this fifth condition is not so new, but recently I know that the notion of AC CPOP manifold. This notion is given by maybe Alfred Gray. What does it mean? If Riemannian manifold, you consider just a Riemannian, then here is a Ricci curvature, Riemannian Ricci curvature. Here, how to write? But here, so this is a cyclic sum of covariant derivative of Ricci curvature. Yeah, and here is this is a scalar Riemannian scalar curvature of Riemannian sense. So if Riemannian manifold satisfy this condition, then Gray said this Riemannian manifold is CPOP. And in today's M is Kaehler, then this reduces in this way. So so this is just this is I know. Okay, so okay. So if we take a conjugate, then this is equivalent. Okay. So this is just okay. So I'll give you how to get to this formula from first one. Yeah. But it's just tensor analysis. Yeah. So just the tensor analysis, but by using we need using this property. Okay, and no. So we need this formula. Yeah. So rich tensor satisfy this. So this is because so rich form is declosed. Yeah. Every Kaehler manifold satisfies this one. So this comes. So by using this property, we take but here so Riemannian curvature tensor appear, and this Riemannian curvature tensor satisfies the second Bianchi identity. Yeah. So this is always this always satisfies this. So this is a second Bianchi identity. Since already satisfied this one. So if you calculate this one, we need to only calculate the second term and the third term. So and by using this formula, by using this equation, and take a metric contraction. How to write? This is just this term. Okay. So if B is Delba-Nabla closed, then we get the last condition, last equation, and so this is how this is just the proving from 1 to 5, and it not too hard to see that the fifth condition implies the first one. Okay. just calculation, and here, so here we have, so this is just, yeah. But B satisfies this equation, okay. So this is just, yeah, okay. Here we put another term here, since metric contraction of B is 0. So, but this is just how to write? From the Kaehler identity. So what I proved now is just the prove from second condition to fifth condition. So so maybe these are equivalent. Yeah. Okay. So of course, if Kaehler manifold is Einstein, then this vanishes, and also this vanishes. So we get this one. So Kaehler-Einstein manifold satisfies this one. Okay. But it's a very, very trivial case, or okay. So this is the first of the my main talks, main result. Okay. And the next one is just okay. So Next one is just next one is just consider scalar curvature condition, yeah, under this hypothesis. Yeah. So next one, so under this condition, closeness of the Bochner curvature, and so consider the conditions on scalar curvature. Okay. If here, so look at this equation. So S is just a scalar curvature. So if scalar curvature is constant, then so right hand vanishes. So this means so each curvature is parallel in terms of the covariant derivative. Yeah. So when scalar curvature is constant, yeah, it's a next of my main result. But so next one is here. Okay, here you have. So here we have a theorem. This is just a Kaehler. Even non-complete, but necessarily connected. And B. So assume. And here, so here, if there exists so positive constant, so I'll explain later what is Q. Q is just a rich curvature. So this is a statement of theorem 2. Now, what is Q? Q is, so here I write. So consider rich curvature tensor, but so raise up the beta bar. So here. Yeah. So this is just a linear transformation of tangent space. Okay. Of type 1, 0. Yeah, okay. So here you have beta, alpha, then you have a, okay. So we denote this one, this operator Q. So Q, Xi. Okay. So this is bit. Okay. And Qk is just k times composition of Q itself. And here, so since Q is just an endomorphism, vector space, yeah, so we can take a trace. Okay. But this theorem is not new, since yeah, okay. So this theorem was obtained already by Professor Wu-Han Ki, and how to write? I don't know how to. From Hak Kim, yeah, appeared in Kyompuk Mathematical Journal. Yeah. They obtained this theorem, but under condition that B is just parallel. Yeah. They give B is parallel. But parallel condition is very strong. Yeah. Of course, parallel. If parallel, then closed. Okay. And also, recently, this is recently another Korean mathematician. Yeah, another Kim obtained the similar result. Yeah, but he assumed B is harmonic. Yeah, he assumed this condition, and same conclusion. Yeah, same. Yeah. But he didn't recognize these properties. Yeah. He only consider this condition. Yeah. And under this condition, he get this formula. Okay. Okay, so this equation is very important. Okay. So now I'm going to give a very, very brief sketch of proof, but I want to omit the detail. Yeah. So, of course, if k is 1, then this is just a scalar curvature. Yeah. So this is trivial. But you need a case, even case, and odd case. Yeah. So there are two possibilities. But odd case is very, very simple or easy to show. Odd case is very easy. Yeah. And the even case is very, very hard. Yeah. So if you look at the paper of Key and Kim, you cannot follow the argument. So I'll try to show by myself in terms of complex or Kaehler terminology. First, we need a lemma, following lemma. Yeah. So you consider this one. This is just a scalar function on M, and take a derivative. So this is just more precisely. Okay. So this is a key lemma, but this is just from this one. Okay. And trace Q is just just this one. So first show case odd case. So we assume this is constant. No. Oh, yeah. Okay, odd case. So k is 2L plus 1. So here is just twice of L. So here you have okay. So we have this one, and taking contraction with yeah. So these are just tensor calculus. Okay. Okay. And so this is just a norm. Gradient of S, 1, 0 gradient of S square. Okay. And this is just so inner product of this one okay. This one. Yeah. So this gives us many informations. So this is so Q twice of L times Q is just a non-negative operator. Yeah. So this trace is non-positive, non-negative, and this is also non-negative, and this is also non-negative. Okay. Okay. So this is just you can write down this into this way. Since Q is just a self-adjoint, okay? So this is also non-negative. So if you assume this one, so consider so subset in M consider this one. Yeah. Consider subset of n in M. If n is empty, not empty, then this is open. Yeah. But this must be 0. Yeah. Since this is positive. Yeah. Right? But this means S is constant on M. But so the fifth condition implies that Rich parallel. Yeah, this means Rich parallel. Yeah. So this is also how to write. This hold, positiveness hold, not only inside N but also the boundary of N. Yeah. So this N is closed. Yeah. But M is connected, so this N is just N is equal to just M. Okay. So this scalar curvature constant. Yeah. So in this way, so if I assume N is non-empty, then we get the scalar curvature constant. And on the other hand, if this is 0, then this means that any eigenvalue of the Rich curvature, yeah, is 0 if yeah. But so this means Rich curvature is Rich curvature vanishes. Yeah. So Ricci curvature vanishes means scalar curvature also vanishes. So scalar curvature is constant, just constant. So in any way, so the case of odd number, it's okay. Yeah. But I just follow their argument. Yeah. But by using so complex coordinate convention or terminology. So here is so I do not want to explain the argument, since maybe you may be confused. You may be confused. But I'll give you atmosphere of the argument. Okay. So no. How to write? Okay. No. They do not use this one. Okay. So they use they looked at this formula, and next they differentiate, covariant differentiate of this one in terms of Nagura tau. Yeah, this one. Yeah. And okay, so this one. Okay, so sorry. And so, but they got some final equation, but here is a final equation. But they take a contraction with and also contraction with yeah, contraction with this one. So they got the foreign formula, but it's not so how to write. So I'll write down final form. So this is 0. so there are similar formula, similar term. Okay. Yes, and finally, so this is the final form of the equation, which they obtained. Yeah. And and look at this. So these are so these are every term of this the right hand side is non-negative. So you can, by using the similar argument as in the odd case, so we obtain that scalar curvature is constant. Yeah. I'll skip the detail of the argument, but so this we get this theorem too. Yeah. And so I'd like to say the final remark. Yeah, one remark. Final remark. I have one question. There exists a Kaehler manifold with derivable closed of the Bochner curvature tensor, but scalar curvature is non-constant. Yeah. No, I'm investigating this question, but Jaeman Kim said that there exists Kaehler manifold satisfying this condition, but I didn't find explicit example of this. So I'd like to stop here.
Thank you very much. Do you have any question or comment?